Have you ever wondered what our sun was like in its early days? Envision when our sun was not the timeless, stable star we know today, however a turbulent and strong power battling to track down its position in the universe. The James Webb Space Telescope, JWST, has begun this strange time, uncovering a universe of inconceivable energy and brutal infinite occasions. Interestingly, we are rethinking our sun and different stars, finding insider facts that could change how we might interpret the universe for eternity. As JWST looks further into the universe than at any other time, it returns pictures and information that are however energizing as they seem to be uncovering. These perceptions not just revealed insight into the fierce young people of stars, yet additionally challenge all that we assumed we had some awareness of the birth and development of stars like our sun. What new secrets are ready to be found? How did the planets, including Earth, form and what forces were at work in the beginning of our solar system? The responses lie in the weak, far-off light caught by JWST, a light that has gone through reality to contact us. Stars are brought into the world in obscurity, thick billows of gas and residue that saturate the universe, large numbers of which are known as star hatcheries. The cradles of star formation are these incubators, where the interaction of energy, wind, and dust produces the celestial bodies that illuminate our night sky. Nevertheless, this procedure is far from tranquil. In these locales, powers are enormous, making outrageous tension and temperature conditions. Young stars are dynamic and powerful entities, as JWST has demonstrated, able to project enormous jets of gas and energy that span many light-years. One of the most noteworthy parts of JWST's perceptions is the savage idea of star arrangement. The telescope gave us our first look at Herbig-Haro objects, which are bright nebulous regions that are associated with newly formed stars. These items happen when floods of ionized gas catapulted by a youthful star crash into the interstellar medium at high rates, making shock waves that produce a marvelous light show, enlightening the beginning phases of a star's life in a manner never seen. Take, for instance, the Herbig-Haro object HH21, which can be found approximately 1,000 light-years away from Earth in the constellation Perseus. One of the smallest and closest examples of these things is this one. JWST's perceptions of HH21 have given an abundance of information, uncovering urgent insights regarding the cycles happening at the beginning of heavenly development. The telescope's capacity to catch the weak light from these far-off objects has permitted space experts to concentrate on the arrangement, temperature, and elements of the gas and residue encompassing youthful stars, offering new bits of knowledge into the components of star development. JWST's perceptions are not simply uncovering the introduction of far-off stars, they are additionally revealing insight into the beginning of our own Sunday. Scientists can draw parallels between these young stars and the Sun during its formative years by studying objects like HH21. The similitudes are striking, recommending that our Sun likewise went through a time of extraordinary action, portrayed by strong plains areas of strength for and. This finding is important because it gives us a look into the past and helps us figure out how our solar system looked more than 4.5 billion years ago. The planets eventually emerged from a disk of gas and dust that likely surrounded the Sun when it was young. We are able to reconstruct the environment in which the Sun and its planets were born thanks to JWST's ability to observe these early stages of stellar evolution. Concentrating on Herbig-Haro objects like HH21 uncovers the difficulties youthful stars face in their initial formative stages. The surrounding accretion disks may be disrupted by these stars' powerful jets, preventing the formation of planets. It raises fascinating concerns regarding the processes that are required for the formation of planets and the factors that influence the development of planetary systems. JWST will assist scientists in improving their models of star and planet formation and bring us closer to comprehending the origins of our solar system by observing these processes in real time. One of the most thrilling disclosures made by JWST is the job of attractive fields in the arrangement and advancement of stars. Attractive fields are a major power in the universe, forming the elements of growth circles and controlling the outpouring of material from youthful stars. New insights into how these magnetic fields influence the direction and strength of jets emitted by young stars have been provided by JWST observations. Attractive fields are vital close to youthful stars as well as in the more extensive course of star development. They are able to direct the flow of gas and dust in areas with strong magnetic fields, directing it toward the forming star and influencing the molecular cloud structure. A star's final mass is ultimately influenced by this process, which is crucial in determining how much material it can accumulate. The ability of JWST to observe these magnetic fields in action has opened up new astrophysics research avenues. By concentrating on the cooperations between attractive fields and star development, researchers can acquire a more profound comprehension of the powers that oversee the introduction of stars and the advancement of heavenly frameworks. This information is fundamental not just for figuring out the beginnings of our Sun yet additionally for anticipating the way of behaving of other star frameworks all through the universe. One more critical commitment of JWST to how we might interpret star development is its capacity to concentrate on the synthetic organization of gas and residue in star framing districts. Astronomers can analyze the elements and molecules in these regions with unprecedented precision thanks to the telescope's sophisticated optical instruments' ability to detect faint light signals. The discovery of complex molecules in the young star's jets was one of the highlights of the JWST observations of HH21. These atoms, like carbon monoxide and silicon monoxide, are marks of enthusiastic movement inside the star and its prompt climate. The presence of these particles in the planes is astounding, giving new bits of knowledge into the compound synthesis and thermodynamic cycles at play during the beginning phases of heavenly advancement. These discoveries have significant ramifications for how we might interpret the substance processes that happen during star development. By concentrating on the organization of gas and residue in these locales, researchers can get more familiar with the circumstances that lead to the development of stars and planets. This information is essential for grasping the beginnings of life, as the components and particles found in star-shaping locales are the structure blocks of planets and living organic entities. JWST's perceptions are not restricted to individual stars and their environmental factors. New insights into the broader processes of cosmic evolution will be gained through the telescope's ability to observe distant galaxies and other cosmic phenomena. By concentrating on the light radiated by far-off systems, quasars, and other heavenly bodies, cosmologists can follow the historical backdrop of star development and the advancement of worlds across the universe. The JWST's ability to see into regions where stars are still in their infancy is one of its remarkable capabilities. The process of star formation is studied in these stellar nurseries, which are dispersed throughout galaxies and serve as laboratories. Stars are more than just celestial objects, they are also the fundamental building blocks of galaxies and the sources of the elements that make up planets and life itself. As a result, having an understanding of this process is crucial. The near-infrared camera, NIRCam, and the near-infrared spectrograph, NIRSpec, of JWST are instruments designed specifically to detect the weak infrared signals that young stars and their surroundings emit. Infrared radiation is especially helpful for concentrating on these districts since it can infiltrate the thick billows of gas and residue that dark star-shaping areas, uncovering the secret cycles inside. The process of accretion in young stars is one of the most important discoveries made by JWST. An accretion disk is a rotating disk that is formed when a young star draws in the gas and dust that surrounds it as it forms. This plate assumes a critical part in the star's development, giving the material from which planets can frame. JWST's capacity to concentrate on the substance synthesis and elements of these circles offers bits of knowledge into how planetary frameworks, including our own planetary group, shaped billions of years prior. The star's energy and the pressure from the surrounding gas and dust must maintain a delicate equilibrium during accretion. Radiation from material falling onto the star gives off energy that heats the surrounding disk and drives powerful gas outflows. Jets, or outflows, are a characteristic of young stars and play a significant role in shaping the star and its surroundings. JWST's perceptions of these planes have given new experiences into the systems driving them. By concentrating on the substance arrangement and temperature of the gas inside the planes, researchers can study the circumstances that win during the earliest phases of star development. This information is fundamental for figuring out the nature and development of stars and planets and for anticipating the cycles important for the arrangement of life-supporting planets. Planet formation also relies heavily on magnetic fields. According to the observations made by JWST, magnetic fields play a crucial role not only in controlling the formation of planets within accretion disks but also in shaping the dynamics of these disks. Attractive fields can impact the heading and speed of gas and residue streaming into the star, influencing the dissemination of material inside the plate and eventually the arrangement of planets. JWST's capacity to notice these cycles in phenomenal detail has changed how we might interpret star and planet development. By concentrating on the cooperations between attractive fields, growth circles, and planes, researchers are revealing the multifaceted dance of powers that brings about stars, planets, and the potential for life all through the universe. We are discovering not only the fundamental processes that shape the universe as a whole but also the origins of our own solar system as we continue to explore the cosmos with JWST.